So yeah, I think my talk is a bit more interesting than maybe the title sort of gives off. And I also am not sure if I'll take the full 30 minutes. So yeah, hopefully there's lots of time at the end for questions. So yeah, just a little bit about me, and that will sort of help motivate the work. So I'm a researcher at scite.ai, and what we primarily do is we look at citation classification. So for scientific research documents, so one paper cites another paper, we take the context and sort of cite it. But one of the areas I'm interested in is sort of more foundational aspects of natural language processing and understanding. And oh, I still have my hand raised. I don't know how to get out of it. Oh well. One of the things that comes up is, and as I'm sure that a lot of you are aware, is that in terms of multilingual NLP, there's sort of a lot of gaps, and the way where I see it in my work is coverage of models that address different languages, especially because we work with Turkish documents, Chinese documents, and so on. There's scholarship in all kinds of languages, and so that kind of motivates why multilingual NLP is kind of interesting, and then and why I'm sort of interested in that. And then I'll go into, actually, before I get to this, I'll just kind of motivate this work. And so there's this core problem in linguistics and natural language processing, and you'll find it come up a lot, but it usually comes up within this subfield called language complexity. And so what language complexity addresses is how complex is a language, and it's very similar to and influenced by what we think of as computational complexity in terms of how long it would take to process say auditory input in terms of understanding it, or reading, or those kinds of things. So it very much is kind of this time and space bound abstract measure for how we understand language. And so I'm going to talk about language complexity and how we compare languages. But first, I'll sort of I'll spoil it and give you the end first, which is basically what I found was in the phonetic transliteration task. So transliteration means when you take a source language orthography, it's writing system, and you transliterate into another, a target orthography, a different writing system. And the phonetic task would be taking a native orthography like English and transliterating it into the International Phonetic Alphabet. Another alternative, which I didn't look at here, would be something like romanizing Cantonese or in Pinyin or something like that. Or writing Arabic names in English would require transliteration. And so what I found was that languages that have the closest ratio of orthographic characters, graphemes they're called, to phoneme ratio are the easiest to learn. And so I'll leave it at that. I'll go into what easiest to learn means later. But I kind of more, and that's kind of what this graph shows. And again, I'll return to it to make it interpretable. But more importantly, I think, for us as researchers wanting to make natural language processing models lend themselves more to different languages and diverse languages, is due to the differences in phonetic and orthographic inventories. And inventories is just the essentially, you can think of it as vocabulary, right? An phonetic inventory is the number of sounds a language lends itself to, an orthographic inventory is the number of characters. We should pay attention to data sparsity across languages and be skeptical about data sets and tasks that are not meaningful. And you'll see why I think that's super important in a second. So I started looking at language complexity, but essentially what when you look at language complexity, it actually is, it's not so simple as saying, well, we're going to compare languages. Of course, we know as natural language processing researchers that language has all these dimensions. And so, there's how complex is a language to learn or understand or read or write or pronounce. And of course, that breaks down into this familiar sort of pipeline view of language that we're all familiar with. There's complexity on the phonetic level, there's morphological complexity, syntax complexity, semantic complexity, even stylistic complexity, which is kind of more similar in my day-to-day work, where scientific research documents are a particular stylistic type of language. But I'm going to be focusing on sort of a more tractable way of looking at language complexity that's been researched quite a bit. And there's a conference that you might be familiar with, SIGMorphon, which is run by the ACL, and they typically try to look at these things from more the phonology, the morphology perspective. But and then within orthography, so study of writing and language writing systems, there's kind of these two tasks that I'm kind of interested in, and phonology as well. There's transliteration, which is what I mentioned before, and pronunciation. And so I'm gonna sort of restrict the definition of pronunciation to something that's tractable to machines. And you'll see how I define that task, or how that task is defined by the literature in a second. So how would you evaluate language complexity? Well, classically, it was an analytical task of a linguist, which if you don't have a linguist background, typically the method here is taking inventories of a language. So this is the scope of phonemes that the language can produce. This is the scope of phonemes another language can produce. So it's comparative, right? And to say something like, okay, well, in terms of an applied linguistics perspective, you might say something like, oh, English speakers have a hard time learning to pronounce these characters because there's tone involved or something like that. So that's kind of like how you would look at language complexity classically. But recent work has sort of looked at understanding a language complexity in terms of how hard is it, or what kind of modeling can we do of reading, writing, pronouncing a set of languages. So essentially, we've reframed the language complexity task, or the cross-lingual language complexity task, into a machine learning task, where we go, okay, can we devise a model that can learn certain well-specified tasks, and then compare the model learned across different languages. And I just put some references here, but they're all in the paper. So the way we can circumscribe this task is we can look at specifically a very popular task called the Grapheme-to-Phoneme task. And it might sound sort of new, but actually many people have encountered this task because it's a critical part of classical text-to-speech pipelines. If you ever looked at any text-to-speech types of things, this is a critical part in at least classical systems, where you have a source input for a language, and then you want to have phonetic output. And here I'm using gnocchi, which is an Italian dumpling, and it's international phonetic alphabet transliteration here, which is supposed to be each of these symbols in the IPA alphabet are like individual phonetic pronunciations. And so the task really is, how do you get from a source language, and ideally a language native orthography, so Italian using a Latin script, to the IPA script. So really that's what I'm going to focus on. That's the popular cast is sigmorphon. And what people tend to argue is that it's sort of a proxy for learning to pronounce. So at the beginning, I kind of said, okay, well, here I'll talk about what I mean by learning to pronounce, and this is kind of our machine equivalent to learning to pronounce, right? There's a lot more complexity in how a human learns to pronounce, namely, how do we sort of go from some mental representation of a phonetic thing to actuating it in our vocal cords and so on. But here's sort of a circumscribed learning to pronounce, where we can from reading, right, from taking a source alphabet. And so the experiment, which if you look at the literature of language complexity under machine learning modeling, you'll kind of see very similar setups. The experiment, which would be, okay, model a Grapheme-to-Phoneme transliteration model across different languages. Here we use 22 languages, which are drawn from the IPA DIC data set, which is a subset of Wiktionary. I'm not sure I pronounced that, but it's like Wikipedia is equivalent to a dictionary, which has widespread international phonetic alphabet transcriptions. And we look at something called a median resource assumption. So if you're familiar with how we sort of look at data sets within across like multilingually, in natural language processing, we usually kind of have these weird buckets of a well-resourced language, which is over 100,000 samples, and then a medium resource language, which is 10,000 samples, and samples being training samples, right, input out pairs, and then low resource, which is 1,000 samples, which I'm not looking at. And so what we do is we in this experiment is we look at character level transformers. So these are classical transformers, transformer models that attention-based transformer models that are going to have inputs that are based on the character and the character set. And so here the character set would be the source orthography of the source orthography of the language to transliterate, and the target would be the or the output would be the international phonetic alphabet character levels. And then we compare character level accuracies per model. So it's when I talk about accuracy later in this, it's character level accuracy. Though you'll see in different sigmorphon, they'll do word level accuracy and different sort of valuation schemes to capture longer longer sequences of words. Here we're just comparing word to single word transliterations, but there's lots of cases where words blend into each other and so on. You might want to look at the words, but that's not looked at here. Okay, so what I said I was going to explain this result, phonetic transliteration. In the phonetic transliteration path, languages that have the closest ratio of character to phoneme ratio are the easiest to learn. And so what easiest to learn means, of course, as I had circumscribed it before, is how accurate can the model get with given the same samples that for each language, right? So here we have the accuracy. This is the character level accuracy, as I said, of the transliteration model, and then below on the x-axis we have the ratio of IPA sounds used to the number of characters in the language alphabet. And before you start thinking like, oh, it's sort of not fair, this is obvious results that we would have in traditional Mandarin that's kind of the lowest scoring given the size of the alphabet. I think there are some interesting things to say here, and in some ways it's a very intuitive result where languages where there's a proxy for individual characters in the language matching one single sound are the easiest to learn, because it's very much along the lines of sample efficiency, where the samples we're using for modeling the data set, it's extremely efficient in the sense that one character only means one pronunciation, and so learning that math is a pattern that's really easily identifiable. And you'll see sort of that English is poor performing, and German as well. And in those languages, we have characters that can have, and this happens in almost all languages, characters that happen to have different pronunciations based on context, or where they appear in the sentence. And so really this result is just showing that intuitive understanding of languages that we sort of already have, where this idea of single sort of one-to-one phonetic languages are easier to learn, and of course for machines in this case. There is one kind of cluster I'd like to highlight here, and it's Vietnamese, which I talk a little bit in the paper, and the Sigmorphin conference, they've also sort of noticed this. There is this idea of expressivity of languages, where a language can, and you'll notice sort of like as we go away from the 1-to-1 ratio of characters to sounds, we have this significant drop off to Cantonese, Mandarin, Japanese. With Vietnamese, there's this idea of expressiveness, where though a language's source orthography, its writing system, could be complex, it's expressive in the sense that like it maps to very simplified pronunciation rules, rules of pronunciation that are quite straightforward. Whereas when we go from a script that's Latin based or is phonetic to a script that is, actually I have a slide on this, but script that is syllabic or abjad, which is Arabic, where the vowels are not in place, or logographic, like Cantonese Mandarin, we have much higher complexity. And so if I look here, this is just kind of numeric representation of what was on the table that we have. Interesting, we have a constructed language, Esperanto, here, but we have Spanish, French, Malay to be the highest performing accuracy ones, and they're sort of the closest in a ratio from 1-to-1 with IPA. Now, of course, this could be more or less a coincidence, right? Where, and if you're native speakers of these languages, or these languages, you'll know that they aren't 1-to-1 phonetic. There are many cases where in French that or Spanish that we have characters that will have different pronunciations depending on where they are and so on. But 1-to-1 ratio, I argue in this paper, is sort of an interesting proxy for what you might call simplicity under the transliteration task, phonetic transliteration. And of course, as I mentioned before, these logographic and syllabic languages, unfortunately, this data set didn't have enough data for more diversity of different types of alphabets, like maybe a syllabic for Korean or something like that. But you can see they tend to perform quite worse. And I kind of alluded to this, but as you sort of go farther from the 1-to-1 ratio, like English or German, you start again to perform poorly. And so the one kind of implication of this is when we look from a machine learning perspective at language complexity, we actually tend to find the same things that linguists do, which is that differences in inventories, the orthography, the number of characters, and the number of pronunciations, they tend to be what distinguishes the complexity of the language. These individual units, these inventories, are basically the main determinant of the model's performance, and that's what linguists have been doing. Oh yeah, and I mentioned this limitation before, which is that inventory ratios are not the same thing. Expressiveness ratios, they're just a proxy for expressiveness or simplicity. And so what I kind of wanted to highlight is when I was looking at this, I was thinking, well, maybe it's just as simple as looking at it from a statistical perspective, where languages that tend to be harder to learn transliteration for, it's just because we don't have enough samples. And I've detailed that here, where for traditional Mandarin, which is the logographic orthography, only achieve 71% accuracy, and of course the details for the experimental setup and model are in the paper. We have in this particular 10,000 word sampled set, we have 23,000 number of unique characters. So we have a number of samples per unique character, which is 0.34%, or sorry, 0.34 percent. So we don't even have one sample per, on average, one sample per unique character, which of course, if you're thinking from a modeling perspective, of course we would not be being able to train a model well. And you can see sort of this trend of accuracy going up when we have a higher number of samples, though of course it sort of saturates where there isn't quite a simple line between the number of samples and accuracy, of course, as you can see in English. So though there is this obvious implication that we should sort of think about and be wary about the number of samples we have when comparing languages. In the case where we compare sort of English and Malay, then there are still these differences that are warranted, I think, that I mentioned earlier, where if, for instance, how phonetic the language tends to be, the writing system tends to be, is probably a result that still would stay. And so because sample size matters so much, I just sort of conclude in the paper that when we're looking at cross-lingual tasks, and here, we're focusing on the GPT task, the Grapheme-to-Phoneme transliteration task, we really should be wary about the differences in languages, differences in inventory. So for us, it's simply the orthography, the source writing system, and the phonology, the number of pronunciation units the language can make. But for other tasks, there might be differences in lexical diversity, like lexical inventories, or there might be pragmatic inventories that are different. So like the number of greetings, for instance, where when we do these multilingual comparisons, and we sort of have this standardized 1,000 is low resources, 10,000 medium resources, 100,000 well resource, maybe that's not a fair way to do evaluation. And maybe and I don't really propose one in this paper, but maybe there is a fairer way where we could sort of normalize these things. And if you think about it, maybe we could do for this task, and unfortunately I didn't have time to look at this yet, but if we did, maybe we would do normalize the data set so we had 100 samples per unique character. Maybe that's a fairer way of doing language comparison. And if we did that, maybe we would have better, more robust ways of looking at languages. And of course, we can't do that in the 1K, 10K, 100K paradigm because we did one for the number of unique characters for Mandarin versus a smaller source orthography like English. It would be very different number of absolute samples. And so future work would just look, I'm thinking of how we would sort of have fair multilingual evaluation broadly, and rethink sort of these language complexity comparisons, and look at, actually, it's kind of interesting to look at, what might be different ways of making multilingual comparisons fairer in terms of inventory on different levels, like syntax or morphology or something like that. And so that's really the presentation. If anyone has any questions, I'd love to take them.